So welcome to this session, Saturday the 6th, here at the Swedish Pavilion. The theme for our pavilion is Pioneer the Possible, or Pioneer the Fossil-Free. And this session will be split in two. First, we will talk about a project in Estonia that will have the possibility to reduce the carbon emissions on a global level with 400 million tons. And that is the equal sum of 8 times as much as Sweden as a nation emits to the climate each year. In the second part, we will talk about nitrogen and how we be able to then take away nitrogen and then in the long run restore the seabeds. Nitrogen, by the way, was invented or discovered here in Scotland, so we are the right place to talk about nitrogen, to be honest. But let's start with the first session where we will talk about calcium carbonate, because that is really the reason why we are here. And to start with, and the battle place here is Estonia. Estonia has since the 1960s, in the way that they have produced energy, used oil shale and incinerated that. And this has created an environmental burden for Estonia. So now more than 600 million tons are landfilled or deposited, you could say, around in the northeastern part of Estonia. Those 600 million tons contains, though, resources that we in the project have been able to make sure that we can bring the resources back. And we will add carbon dioxide as a part of that equation. When it comes to circular dimension, and just let me elaborate about what's happened at the COP25 in Madrid. I talked with a lot of people about, in the closed sessions, about the need to create circular material flows. But the challenge was that in the open floor, there was just discussion about reduction of carbon dioxide. At this COP, 2 years later, here I see that everybody talks about circularity. And Professor Johan Rockström, together with Sir Richard Attenborough, did in their movie that they also broadcasted this summer, Breaking Boundaries, the Science of Our Planet, highlight that circular material flows will not only reduce the carbon emissions so that we will be able to fulfill the agreements in the Paris Agreement, but also to support that we can overshoot any of the other planetary boundaries as also. So circularity, I think, will be on the agenda going forward. I will not deep dive anything more into that. I would now like to introduce you to Alar Saluste. He's the project manager for our project in Estonia, and he works for Ragn-Sells, of course. And he will now guide you what is the innovation we are talking about and what is the plan going forward. So over to you now, Alar.
Thank you, Per. And good morning to everyone from Glasgow. So before we go to this white powder that I have on the table, I would like to talk about a little bit how we are getting raw materials today. So in principle, majority of the materials like copper, iron and other raw minerals are being produced by digging up ore, which usually is quite diluted. So for copper, for example, it's 0.2% of copper in the ore, and then the valuable part will be extracted and the rest will be waste. And this way we are basically from 1 ton of mining we produce only 0.2 tons of copper. In Ragn-Sells, we see that in order to fight the climate change and to bring on circularity, we need to look differently materials. As our history is recycling of waste, we are mainly looking at waste materials, which would enable to make or build circular loops for materials. And we would like to approach extraction of those materials differently. So instead of going for one valuable part, we would like to start from the logical one. What do I mean by logical? For example, there are certain types of hazardous waste that have a great opportunity. And meaning that the part that makes the waste hazardous is actually opportunity. It's a logical start for material extraction. And I've heard on this event in Glasgow and also on this stage a few times that you should dream big, but start small. So we are dreaming big. We want to reach zero waste from such materials. But we are starting small. So the good example here is the Estonian project, where we are extracting the reactive part of oil shale ash. So the reactive part is calcium. If you take the ash to your hand, it slowly starts to react with your hand. By removing that part, we are making the waste stream inert or less of a burden to the environment. And also, once we have taken out the calcium, we can take CO2. As Per mentioned, we have 600 million tons of deposits, meaning that potentially we could capture 400 million tons of CO2 into this nice white powder. So we have calcium, we have CO2, and we can make calcium carbonate. And as I said, this is just the start. The first reactive part is calcium, but what is left in the material, or the leftover material, is a brand new opportunity to extract silica, to extract magnesium, two of the materials which are in the critical raw material list. Also aluminium, potassium, and other smaller parts. But in order to go there, we need to first have a commercial production of calcium carbonate, and then we have an opportunity to go further. What is also important here is that because we are using two waste streams, we are using CO2 and we are using ash. Our production and our product will be CO2 negative, so with a negative CO2 footprint. If you use it in another material, like in the mix for PVC mix for windows or in the flooring, and they will have a nice example of a flooring company later on. Then this filler will reduce the footprint of your product, CO2 footprint. What is also important about two waste streams is that working with waste and for circular solutions, we have seen that today's legislations are not ready for such things. We are set for linear economy, and that means there are plenty of challenges also from the legislative side. For example, getting the actual CO2. Which kind of CO2 is okay for our project to use, and of course all kinds of permitting. So to summarize, what we want to do is we want to look at totally new way of how we are getting raw materials. Instead of extracting just one part, which could be today the most valuable one, we want to systematically use the waste into zero. And we have one good example from Estonia. But as I said, this is just a start.
Thank you so much, Alar. Today's production of PCC are done through that you are mining limestone. You dig it up from the bedrock, you incinerate it, because you need to take out the carbon dioxide, and then you produce the PCC. So we have a double profit here for the climate. Avoid digging up limestone at the same time that we will use carbon dioxide, and that's the big effect why we have such huge carbon emissions potential in this project. Last week I did have the honor to have a climate discussion and climate talk together with the Prime Minister of Estonia and the President of Estonia, and they were really clear. We will do the Pöxit. That means that we will exit today's energy production. So there will be no more ashes. But the importance going forward is that we need to make sure that we can restore the lands of northern part of Estonia. So this is the aim for the project as well. Make sure that we can take away the ashes, and here we have a 2070 vision. But it depends on that we can have an understanding that we need to source the carbon dioxide, and then of course we need to find more partnerships with others that will use or need to use the magnesium or the silica or the other things that we can extract from the ashes besides just the calcium. There was one other person also that we did discuss with last week, and that was the Energy Commissioner for in the European Parliament in the European Commission, and that's Kadri Simson. So I think we will let her conclude her findings and her ideas about this project. So please now, if you can broadcast the film with Kadri Simson.
We need new, smarter ways of doing things. I'm therefore always glad to participate in events that showcase solutions that are both practical and exciting, bringing our climate and environmental goals one step closer. The oil shale ash project Ragn-Sells has been developing and is presenting today at the COP is a fascinating application of the carbon capture and utilization technology, a technology that is key to our decarbonization effort. I am, of course, especially happy that this project is located in my home country because I know firsthand the issues you are trying to solve with it. Ida-Viru County needs and deserves initiatives like this. Now, let me tell you why I just said that carbon capture, utilization and storage is so important for us in the Commission. The European climate law that entered into force in July this year made our goal to achieve climate neutrality by 2050 legally binding. In practice, this means that all emissions, even those very hard or very expensive to remove, will have to be somehow reined in. This is where CCUS technologies come in. First, these technologies will be particularly important for the sectors where other alternatives for decarbonization do not yet exist or are very expensive, like in the cement or steel production. For these hard-to-abate sectors, CCUS could be the most cost-efficient or even the only way of cutting emissions. Second, some sectors of the economy could never eliminate their emissions. They will continue to occur, say in agriculture or some industries. Even if that is the case, we can still achieve climate neutrality. When the CO2 could be captured and permanently stored, we would be able to create carbon removals that balance the emissions left in the system. Third, significant quantities of hydrogen will be needed for some hard-to-carbonize sectors, for example, steel making, chemicals, or refineries. The ultimate objective is to use only green hydrogen from renewable sources. However, blue hydrogen produced with carbon capture could become a good bridging solution, actually speeding up the creation of a hydrogen market. Finally, captured CO2 could be used in products such as chemicals or building materials. This is precisely the purpose of Ragn-Sells project, turning the old heaps of oil shale ash into a useful chemical component with captured CO2. It is a great example of carbon circularity.
Very strong message from the European Commissioner. So then it's a question, what do the markets say? What will the market? Are they interested in this project, and can we create circular loops? So therefore we'll now go to Paris and talk with the Chief Sustainability Officer for Tarkett, one of the largest flooring companies in the world. And I see that we have now Arnaud Marquis with us. So please, Arnaud, what is your view?
Good morning, everyone. I'm very happy to be with you today. At Tarkett, we manufacture floorings, be it vinyl, carpet, linoleum, and artificial turf, just to name a few. And most of our product, most of our floorings are used in the building sectors. And the building sectors today is having a very strong impact on the greenhouse gas emission, because I don't know if you know, but more than 40% of the emissions, greenhouse gas emission in the world, are coming from building sectors. More than 60% of the waste are also coming from the building sectors. So on top of that, if we look at what says the United Nations says that in the coming 40 years, every 2 weeks, we will build the equivalent of a city of Paris, while we already lack resources. So if we look at the way we work today, we extract, we manufacture, we consume, and then we waste. That's what we are calling this linear economy. For Tarkett, this model is over. If you take a typical flooring, the carbon footprint is due to extraction, 40%, 45% of the carbon footprint, and 30% is due to incineration. So by shifting from a linear economy to a circular economy, we can save up to 80% of the carbon footprint of the flooring. Now, every day we buy products that are supposed to be recycled. But let's look at the reality. What we face is that most of these products are sent to incineration. If you take the example of a carpet, only 7% are recycled. The rest is sent to incineration. At Tarkett, our teams are working every day to seek for solutions. And it works. We have already demonstrated that we can innovate in carpet. We have developed a product, a carpet, that we can fully recycle. In fact, what we do is we take the different layers of a carpet at the end of its use. We separate these layers. The yarn is sent to one of our suppliers who can recycle and produce new yarns. And the backing, the backside of the carpet, is recycled in our factory with a specific technology that we have developed to be able to reproduce, remanufacture backing. So we have done similar kind of, I would say, eco-design and developed similar kind of technology in the vinyl product as well. So that's one example. Eco-design can be very powerful, and we have demonstrated that with specific technology, we can recycle our product. On top of that, we have developed a specific supply chain to collect the product at either when they are installed, because we produce some waste also during the installation. So we can take back this waste and recycle them into our factory. We are also now working in order to take back the floorings at the end of their life to recycle them. And in the past 10 years, we have collected the equivalent in weight of 11 Eiffel Towers. So we have solutions. We still have, of course, a lot to do, but I believe we have been able to demonstrate that it can work. We can shift from linear to circular economy. Now, it's obvious that we have to accelerate, and because we don't have time, as simple as that. We must collect much more. We must develop new technologies. We must make all our products easy to be recycled. And for that, we need to deploy additional resources. We need also to cooperate. We need to cooperate much more than what we have done in the past. And we are already cooperating with other industries because we collect some waste of other industries. In the automotive industries, for instance, we collect PVB, so which is a layer which is in the glass of the cars. And thanks to this PVB, we can produce new floors. We also collect products from the pharmaceutical industry that we use in our floors. And I believe this example, the great project that has been developed by Ragn-Sells, is another excellent example that demonstrates that we can convert a waste that has been accumulated during decades into a product that we can reuse. In our floors, we use a lot of calcium carbonate. So as you just explained, with the process that you have developed, you can convert this ash into calcium carbonate. The good news is that we need it. And the good news as well is that by doing that, of course, we clean the environment, but we also reduce our carbon footprint because this calcium carbonate will contain the carbon that have been captured during your processes. And the good news is that because we are going to recycle our floors, this raw material will be and will stay stored in our floors during decades. So definitively, this project for us is a very good example, and we are very happy to be part of this project because it demonstrates what we are working on every day, that we can shift from a linear to a circular economy. And by doing that, it's also extremely powerful to reduce our greenhouse gas emissions, to reduce our carbon footprint. So I would say very, very happy to be part of this project, Pers.
Thank you so much, Arnaud. There will be some space for questions. If someone would like to take his question, there's a possibility. But I will first ask the question to you, Alar. A reflection of what you heard from Tarkett and Arnaud, and of course reflections from the European Commissioner.
Thank you, Per. My reflection would be that I guess we don't have time, and in order to really reduce the impact on climate, we need to work together. We need to put the focus on the right things. So we start from the most logical, as I said, with the materials, and then we need to move on. Take small steps, but keep moving on. And this is the only way we can save the planet.
So the question then, you hear now that Tarkett have the ambition to create circular loops. So that means that the product that you are producing will be looped over and over again. What do you say about that? Is that the future? You see that from other companies as well, or are Tarkett unique in this way?
For sure, Tarkett is in the forefront, but there are also other companies who are looking into circular loops, and there are many challenges there to overcome, as I also mentioned, because becoming or using waste as a raw material is not a straightforward process. But we have also, with the project, window profile manufacturer has joined. So Gealan from Germany, who is also using the calcium carbonate. And they are also a very good example. They want to become circular, and they're taking the first steps, same as Tarkett. Small steps to the big goal.
Arnaud, any reflections from your side, from Alar, what you said, or from the European Commissioner?
I can only agree with what you said. It's small steps, and by cooperating together, we can do these small steps faster. That's extremely important because, as I said, we need to take back our product at the end of their life. But our products are made to last. Our floorings last between 10 and 30 years. So if we are not supported by people who are in charge of renovating a flat, an apartment, an hospital, to let us know that our product is ready to be recycled, then in a way we will have worked for nothing. So we must cooperate together. We must develop this new supply chain. We must demonstrate that it can be also, in a way, cost efficient, so which means that we need to avoid additional costs due to sorting and so on. But we have also technical solutions. It's not like, I would say, dreaming about something. I believe we have already demonstrated that it works. So cooperation is definitively the only way to be as fast as we need.
And I know also that there is a company in Sweden with the name of IKEA that has also taken up their old floor and sent back to you. And that's an example of also a company that has a real strong circular agenda. So there will be a market, and you are a front runner. That is what we hear here from the stage in Glasgow as well. We do have a question here, so please say who you are and your question.
Thank you very much. Very interesting presentations both. And my question is perhaps to both of you together. My name is Vimal Mahendru. I'm IEC ambassador. IEC is International Electrotechnical Commission, a totally different industry. So I'm just wondering, how do you scale up what is presently, as I hear, an innovation from Estonia or let's say France? You gave an example from Germany also. But worldwide, look at the thousands and thousands and thousands of carpets that are used and replaced also. How do you really scale up and make a difference which is truly global? Thank you.
We first go to Alar and then we take Arnaud.
I think from the filler point of view is that this Estonian project is a good example, but the similar logic can be applied to many different wastes. So it can be scaled out globally, but we need to take small steps. We will do first a demo, then a commercial production in Estonia, and by that we can kind of move forward. Using the same logic, extracting the materials that are most reactive and leaving zero waste in the end.
And you are asking for partners to the other elements as well. So if anybody is listening here, silica, aluminium or magnesium, we will love to talk with you going forward.
Absolutely.
Arnaud, reflections or answers on the question?
So how do we scale up? I would say, again, step by step. We have already developed specific technology. We have a unique technology, for instance, in Europe, to recycle the carpet that we have designed. So this equipment is existing, and we are planning to invest in the coming years in order to increase the capacity. Then we have also the possibility to export this technology so that we will be able to use this technology in other countries where we are selling also the product. Now we have also to take into account, and that's a fact, that we have to take into account the maturity of the different countries. To be able to scale up, to be able to make such a transformation from linear to circular economy, we need to invest. So this transformation is costly. And again, let's be realistic. What we face is that many of our customers are not yet ready to pay a premium in order to get this product that can contain more recycled material and that can be recycled. So it's a level of maturity. So it's also a level of regulation. Of course, if there is a regulation that push the industry to use what's available, this scale up will be faster because we will have the possibility to invest with a pay. So that's I would say a convergence of different things. The first one, have the right product that can be recycled, the technology that can recycle it, and then I would say the demand on the market or the regulation that can push and accelerate the increase of demand.
Okay, thank you. So standardization, procurement, and of course make sure that there is a market, then we will create the market demand. There's a quick reflection here, and then we have Professor Sutton to ask a question as well.
Yeah, just to add to what Arnaud was saying is that you need to start, small steps are one product, one circular loop, prove it, move on. That is kind of the key. You need certain countries and also certain companies need to lead the way. I think Tarkett, Ragn-Sells are leading the way into this kind of thinking, and I believe others will follow and the legislations will follow once that's done.
Professor Sutton, we will soon see you on the stage talking about nitrogen, but you have a question here also.
Yes, I'm particularly interested in this presentation about the carpets, and you mentioned about a product life of 10 or 20 years. And I'm thinking about how one can really mobilize the person who's had the carpet for 20 years to go back. And I'm thinking about firstly, the mobilization, and secondly, the supply chain of that recycled? Because I can imagine they might just call it a carpet at that point rather than one of your carpets. And does that mean that actually what you've got to develop is technology to be able to recycle everybody's carpets generically, or is that too hard? So I can see that back end is really a challenge yet. What's in it for me as a carpet holder to give you my carpet back afterwards?
Okay, Arnaud, that was a question for you.
That's a good question, and that's what I'm saying when I'm talking about let's face the reality. So the reality is that when most of the carpets that are installed today have not been built, they have not been designed to be recycled. So which means that unfortunately most of this will go to either landfill or most of the time to incineration. So that's the reason why we have to act quickly, because we have now the product that can. We have the technology in place. It's not just a promise. I mean, it's a reality. So unfortunately, for many products, it will be talking about carpet. There will be limitations, and it will take 5-10 years to be able to really see a step change with a reduction in waste due to the carpet. That's the reason why we need to act now. Now, this is carpet. We produce and sell carpet, but we also produce other kind of product, like vinyl product. And we have also developed a process in a factory in Sweden where we have the possibility to recycle vinyl, but also the vinyl coming from competitors. So we are also very much aware that if we don't want to wait 10, 20 years to see a difference, we need to develop solutions that will allow us to clean, in a way, the market, take back the waste, not only from the product that were produced by Tarkett, but also the product that were produced by others. This is not, again, this is very, very exciting. This is a challenge, quite important. But our teams are demonstrating, identifying new solution, new technical solution, demonstrating that this is something that we can expect. So in the coming years, I'm quite sure that we will have the ability to take back very important quantity of product from the market, even though it's not produced by us.
Okay, thank you so much. Thank you, Alar, and also thank you, Arnaud. We will now switch into the second part, and here we'll talk about nitrogen. And I just yesterday was also teach that nitrogen, the birthplace, not for nitrogen because it has been here for forever, but discovery of nitrogen was done here in Scotland. So therefore I'm very pleased to have honor to invite Professor Mark Sutton that will give an introduction to the nitrogen challenge that we are facing. And I think that if he can also explain more about how it was discovered here in Scotland, I would appreciate that as well. So please take the stage, and you have at least 10 minutes to elaborate on nitrogen.
So thank you very much, Lars. It's a pleasure to be here. I didn't have to come far like many of you. For myself, it's just across the other side of Scotland. Sitting here reflecting, and also reflecting on the discovery of nitrogen, I'm left with a thought that we don't always notice the important moments. When is the important moment? Sometimes you do, sometimes you don't. And I think this time at COP, whether the big agreement is made on carbon or not, I think there is an important moment happening. This presentation you've just been seeing about circular economy is much wider than just purely a carbon dioxide discussion. And that's why I'm really excited about this moment, which is here at COP, because we're going beyond purely talking about carbon. So think about the three main greenhouse gases: carbon dioxide, methane, and nitrous oxide. There's a methane pavilion right next to us here. You see it, the methane moment. We're just emerging into that nitrogen moment. So 250 years ago, next year, but maybe he made the discovery in the winter, who knows, Daniel Rutherford Daniel Rutherford was a doctoral student of Joseph Black. Joseph Black was the man that discovered carbon dioxide in Scotland, in Edinburgh University. And Daniel Rutherford was doing his thesis on carbon dioxide. He was working on carbon dioxide when he discovered nitrogen. He discovered the gas dinitrogen. That's 78% of every breath we take is pure nitrogen, N2. It's unreactive. It doesn't do much. It gives stability to the atmosphere. If we didn't have that nitrogen, we only had oxygen and carbon dioxide, we'd be burning continuously. There'd be such a flammable atmosphere. So it's giving us the stability we need. And in Daniel Rutherford's thesis on carbon dioxide is only 4,000 words. But there are 100 words only where he discovers nitrogen. And I think at that moment, I'm not even sure he realized the significance of his discovery. He was a chemist, he took air and he depleted it of the oxygen, either by passing it over hot coals or letting animals breathe it until it was just left with the carbon dioxide there instead. Secondly, he passed it over lye, potassium hydroxide, to remove the carbon dioxide. So he was left with a gas. He didn't really have a name for it. He called it malignant air. And this malignant air had no carbon dioxide in it, no oxygen. Things couldn't live in it and things couldn't burn, but it was something that was left. And that was then this moment. And I think he didn't realize the significance at the time. It took many years later until it was finally called nitrogen, or in French, azote. Azote means without life. Without life, because you can't live in pure nitrogen. And that's where it gets really exciting, because nitrogen is this juxtaposition between you can't live in it, and yet it's the thing from which life is made. So once you convert that dinitrogen into nitrogen compounds, like ammonia, that can be in a fertilizer factory, Haber-Bosch process, can be in biological nitrogen fixation with special bacteria, and you produce ammonia. And from the ammonia, you produce amino acids. From the amino acids, you produce proteins. The proteins make the enzymes. The very essence of DNA has all these nitrogens running through it. So how many nitrogen molecules are there in the world? Well, think about this. Every DNA is different by definition because we're all unique. So there is a nearly infinite amount. Every bacteria has different DNA. So there is a nearly infinite amount of these nitrogen compounds, just like carbon. And you could say that carbon is giving the structure of life, but nitrogen is giving the diversity of life. So there we are, we've discovered nitrogen, we're discovering it again here at COP, this move from it's not just about carbon, there is this thing nitrogen too, and why should we be caring about it? In the European nitrogen assessment, we summarized it initially to 20 and then down to 9 and finally down to 5 big issues: water pollution, air pollution, greenhouse gases, ecosystems, and soils. And so essentially, nitrogen is affecting all those problems we know about already. Give you an illustration. Yesterday we had a paper in the journal Science. We were very happy to get in that journal. What were we saying? That air pollution from ammonia leaking out from agriculture and nitrogen oxides, actually we've put a lot of effort so far into controlling the nitrogen oxides from vehicles, but very little effort in controlling that ammonia from agriculture. For the world overall, we're estimating 23 million years of life lost. That's a lot of years of life lost. 23 million per year, or 400 billion US dollars equivalent of health damage due to this nitrogen air pollution. And we're showing that it's actually 10 times cheaper now in the world to control the ammonia from agriculture. That's a massive story. When we add up the cost of that, it's even bigger than the nitrous oxide costs. Come to another nitrogen form, the nitrous oxide. It's a greenhouse gas. It's 2 nitrogens together with 1 oxygen, very stable, absorbs radiation from the atmosphere. 6% of global greenhouse gas emissions, roughly. But does it get 6% of the attention? Certainly not. Perhaps 0.0006% of the attention. And clearly, we will not get to net zero unless we take action on the N2O. And that's why we then get to an interesting thing, because the nitrous oxide is a very small part of the nitrogen cycle. It's just a little molecule, but a lot on greenhouse gas. And the technologies to reduce nitrogen oxide specifically is rather difficult. In industry, some sources specifically, but in agriculture, wastewater, much harder, because it's permeating through the system. So if we want to really reduce nitrous oxide, we can't just focus on N2O itself. We have to grasp the entire nitrogen cycle, make the entire nitrogen cycle more efficient, reducing the wasted nitrogen resources. Now, nitrogen resources, we come in, there's a little bit from lightning, but a lot from fossil fuel combustion, there's nitrogen oxides, a lot from fertilizer manufacture, also biological nitrogen fixation. Of all those sources coming in, 80% is wasted as losses to the environment, as denitrification back to N2, as ammonia, nitrogen oxides, nitrate, all those are being lost to the environment. So we're saying, actually, to control that nitrogen oxides climate warming, we're going to have to transform the world's nitrogen cycle. So this is the moment. Here we are at COP26 talking about now let's start transforming the world's nitrogen cycle. And when we do, not only will we make the system more circular, more efficient, but we'll have the benefits for all the other issues. That means cleaner air quality, a better water quality, less impact on biodiversity, all at the same time. And it's hugely valuable. The fertilizer industry in the world is worth something like $300 billion US. Now, if I just value the nitrogen that's lost in the system, lost to the environment, multiply that by a fertilizer price nominally of $1 per kilogram nitrogen, we get $200 billion US worth of wasted nitrogen resource. In the Colombo Declaration, it says the countries have agreed, 14 countries led by Sri Lanka here, have delegate from Sri Lanka in the audience. Let's look towards a goal of halving nitrogen waste by 2030. That's looking to then save $100 billion US worth of resource. Now, there's a resource opportunity there for companies like yours to get going and start investing in. Now, that policy world, we've taken a step with India leading at the 4th United Nations Environment Assembly. They agreed the resolution on sustainable nitrogen management. That's leading to the development of a convention process, inter-convention nitrogen coordination mechanism, getting the climate convention, the biodiversity convention, the air convention, talking, working together with the countries. The Colombo Declaration goal is there to mobilize and make things happen. What we're saying is we're entering the nitrogen decade. If we're going to get to 2030, we have to go faster. Yesterday was launched the Nitrogen for Net Zero text, hashtag nitrogen #4 net zero proposal by the government of Sri Lanka that says, let's get that on the agenda in the United Nations Framework Convention on Climate Change. I'm not going to say too much about solutions because you've said a lot about solutions, but it's about agriculture, wastewater, combustion. Think about a catalytic converter in a car. What is the catalytic converter doing? It's reducing nitrogen oxides. But that nitrogen oxides actually is a resource. You've taken energy to make it, and then you're destroying it again. The same in wastewater. In a wastewater plant, you've got nitrogen in the water, you take energy, and you destroy that resource and convert it back to pure dinitrogen. So you're deliberately spending money to waste that resource. So we need to go back to circular systems, reduce the losses, really simple measures in agriculture. If there's a new motto I'm thinking of for now, it's just called put a lid on it. If you're a farmer and you have a manure pile, put a lid on it. Because if you can smell your manure, you're smelling the goodness being lost, the nitrogen being lost. That is the waste that's happening. That also means that we need to catalyze change. And how are we going to catalyze change? That means investment is needed. There's a conversation we need with the world's financiers, not just about climate finance. What does nitrogen finance mean? Nitro finance. Nitro finance to save $100 billion US per year. So that's our goal. I hope that here in COP26 we're going to see it happening. I'm really excited to see EasyMining and other companies starting to embrace this goal. Wastewater treatment that is not working to spend money to destroy a resource, but working to recycle it, make the whole system more efficient for better air pollution, water pollution, climate change, all together. And with that, thank you.
Thank you, Professor Sutton. I think I will always need to applaud you, but we do that later. And we will now go into talk with Anna Lundbom, that is Head of Marketing for EasyMining. But please stay on the stage because we're going to have then a questions and answer session in the end. So Anna, please go ahead. And I know that you will cover what we see as the problem, but also a possible solution. So the floor is yours, Anna.
Thank you, Per. And thank you, Professor Sutton, for the great introduction to this part, for the very good speech. Well, I'll actually start to repeat some of the things that Professor Sutton said. So if you want to show the first slide that I have, I would be very
Yes, we'll
glad.
put the first slide up.
Perfect. What we see, and as Professor Sutton said, we have a linear material flow for nitrogen, as we have for many other resources, for almost all our resources at the moment. And if we are serious with creating a sustainable and climate neutral world or society, we have to reuse the nitrogen or the resources that we already have over and over again. So if we look at the nitrogen material flow, we, as Professor Sutton said, first extract nitrogen from the atmosphere using a lot of energy, which many times are based on natural gas, and therefore creating significant greenhouse gas emissions. We then use the nitrogen in the society, and quite a lot ends up in wastewater treatment plants or in other waste streams or liquid waste streams. When it comes to the wastewater treatment plants, just as Professor Sutton says, we today remove it in order to prevent eutrophication, and we convert it to dinitrogen, which is released back to the atmosphere. So we have to do the whole thing over again, extracting it with energy and significant greenhouse gas emissions. But in the wastewater treatment plant, when we are using the technologies that today exist, we also have emissions of nitrous oxide when the technology is not going the whole way, not working fully. So this is what we want to change. What we want to do is to create a circular loop for nitrogen so that we reuse the nitrogen that we already have extracted in the society, in, for example, mineral fertilizers, instead of releasing it back to the atmosphere. You can take the next slide, please. Our technology is a two-step process. In the first step, we catch more than 98% of the ammonium nitrogen in the wastewater stream. And we do this without releasing any nitrous oxide. In the second step, we convert the caught ammonium nitrogen to a clean ammonium salt. And the chemical that is used to catch the ammonium nitrogen is regenerated and sent back to the first step in the process again. So here as well, we are creating a circular material flow and preventing new climate emissions that would happen if we need to produce chemicals for each loop. The ammonium salt that we produce is possible to use in, for example, mineral fertilizers, where they would replace nitrogen or ammonia that today is produced, as I said, with a lot of energy and significant greenhouse gas emissions. Ironically, however, we are not allowed to use this clean ammonium salts in mineral fertilizers, since we today have a legislation that is linear, and that is for many materials, not only nutrients, but also for nutrients. We need to have legislation focusing on quality, not origin. Today's legislation is focusing on origin, not quality. So with our chemical process, we efficiently remove nitrogen from liquid waste streams with a high concentration of ammonium nitrogen. And as I said, we do this without any nitrous oxide emissions. We also use less energy that otherwise would be needed in order to produce ammonia for mineral fertilizers and to remove nitrogen from waste streams in order to prevent eutrophication. We are at the moment demonstrating this process in a project financed by the EU LIFE program. And the project will be finished in summer 2022, so we're soon there. We're not only validating the process in the project, we are also validating the climate impact and the energy and the resource efficiency. Another step is to actually validate if we can split the two steps in two different plants in order to try to make economy of scale which is crucial for production and is which is hard for many circular processes today, since the input material is scattered in the society in many places. And that's a big difference from producing virgin material, where the input material many times are gathered at a few places. We see a great potential for this technology in different application areas, wastewater treatment plants being one of the biggest application areas. Otherwise, we see application areas as landfill leakage or biogas production, and maybe even animal farming. We see that this technology has the potential to create a circular material flow for nitrogen at the same time as improving the climate footprint. As I said, wastewater treatment plants is one of the application areas where we see the greatest potential. And therefore, we are very happy to have a wastewater treatment company in this project as a project partner. As we've highlighted before in the COP, partnership is crucial to get circular solutions. So therefore, now we will listen to Dennis Thornberg, Development Manager at Biofos, explaining to us why nitrogen removal and recovery is crucial to them and to the society. Thank you.
So
Hello, my name is Dennis Thornberg. I am the Development Manager in Biofos. And Biofos is the utility that treats all the wastewater in Copenhagen, Denmark. Wastewater contains all the compounds that we humans flush or lead to the drains. Among these are nitrogen, in a form that could be used as a fertilizer. In the old days, the toilet buckets were collected and taken to the fields, so the nitrogen returned to the natural nitrogen cycle. This is not possible today from large cities. The risk of spreading disease is much too big. This is why we have the wastewater treatment plants. So the large cities have a very large accumulation of nitrogen that will cause eutrophication when it's led to the receiving waters without any treatment. So this is actually why we are removing nitrogen, and we have been removing nitrogen in Biofos for 25 years. The method we're using today, the biological nitrogen removal, involves the use of energy, and the nitrogen gets lost to the atmosphere. So we find the option of recovering nitrogen very interesting. And if we can produce an ammonia product that could actually be used as fertilizer, that would be very interesting too. The advantages for Biofos is that for every kilo of nitrogen we recover, we could actually save about 1 kilowatt of power. Potentially that could lead to a saving of about 2 gigawatt hours per year if it would be realized in all 3 Biofos treatment plants. Furthermore, the capacity of the biological wastewater treatment would actually be increased significantly, and that would mean a lot in our already partly overloaded plant, one of them. In conclusion, this climate-friendly process is actually that is closing the nitrogen circle is of high interest and relevance for all wastewater treatment plants in the world. Thank you.
So impressive words. Less energy when you don't need to produce the nitrogen from the atmosphere. Less energy that you need when you need to take it out of the wastewater. And of course, we don't need to emit any laughing gas emissions to the atmosphere. That's interesting. I would like to, if it's possible for you, Professor Sutton, to elaborate on what you heard here from Anna and also from Dennis Thornberg.
Yeah, I think the key thing is to see that it's happening. It seems to be happening at speed. It needs to happen at speed. And I think one of the questions I have is back to you guys is the barriers to that. And one of the barriers which was mentioned was that you can't actually sell the product yet because it's not yet a permitted product. That is, of course, completely bizarre. But essentially you're producing ammonium sulfate. Ammonium sulfate is not a radically new project. It's one of the first ever fertilizers used on plants in the 19th century. First ever trials at Rothamsted were with ammonium sulfate fertilizer. So this is a well-known product, but I think what they're saying is the way in which it's made from recycled products, it's not yet been approved. And clearly, getting that regulatory platform moving fast is vital. We can't wait for another 10 years to simply allow a recycled form of ammonium sulfate to be made. That is completely bonkers. So how to accelerate agreement in the European Union? I understand from previous conversations that there may be a fast track by using a national exemption in some way to do a sensible thing. But we need the whole of Europe to be enabling this kind of technology. I think the other question, which is not entirely clear to me yet, is, I'll call it the payback period, because obviously investment is needed, capital is needed. And we know that wastewater is a problem, but we don't want to see it as a problem. We want to see it as a resource. I would love to see this as a functioning business in which people are making profit, and look at it in the sense of how soon to profitability, considering the capital costs, the build-up costs, and ultimately the resources being generated. So I have more questions than answers, I'm afraid, but I think it's very exciting.
So let's continue the dialogue after this as well. Do we have any questions from the audience? Anyone that will state something? Yeah, we do have a question.
Hi, I'm once again asking this question, and I'm almost embarrassed to ask this. Why is it that we have not heard so much about nitrogen and how to recycle and capture it? I mean, I'm embarrassed also because this is the first time I'm hearing it over here. Thank you.
Yeah, I think I can give an answer to that, I think, because I've been trying to sell nitrogen, the idea, for the last few years. But it takes a while for it to come out. And I think in 2019, when we had the first ever resolution on sustainable nitrogen management in the United Nations Environment Assembly, why did it take 2019 to get the first ever resolution? That's ridiculous. And I think it's because of specialization. We got out of the Stone Age by specializing. And we keep specializing. Scientists specialize, policymakers specialize. So essentially, you've got wastewater is one world, and you're thinking of it as pollution. The mindset is wrong. This is just pollution. We need to get rid of it. And in another world, you've got your factories with fossil fuel burning, creating nitrogen oxides. Those guys are never talking to the water people. That's an entirely another world in this fragmented problem. And again, they see NOx as pollutant. We should get rid of it. So what we started doing, and I think really in the European nitrogen assessment, we said, right, we're going to get all the scientists working together across the nitrogen cycle, the air pollution, the water pollution, the climate change, the biodiversity, the stratospheric ozone people, and gradually getting them together. And in that process of coming together as scientists, we've realized that the solutions have to be together. I spent a long time in the Air Convention in Geneva, trying to get regulation on ammonia, well, they are trying to get, and we are as scientists informing them, seeing huge barriers to action because the farmers just complain, oh, leave us alone, don't regulate us. And so what's gradually become clearer is that if we go away from that fragmentation and come together, we have a much more powerful story. I still face problems in ministries, even in my own country, where the ministry is so big that the air pollution people are so busy and the water pollution people are so busy and the climate people are so busy, and in another ministry, and they can't possibly talk to each other. So this is why we have to bring it together. And what I think the next step of when we brought it together was looking at the sum value of the total nitrogen losses and multiplying it by the dollar value and finding out that we're wasting $200 billion per year of resource. It's just a dumb thing. So I think the answer is fragmentation. And this is why I know not much about wastewater, but it's within the philosophy that we must join up, work together towards a circular solution for nitrogen.
Thank you so much. And we are now...
Can I fill in there, Per?
Yes, of course, Anna.
Yeah.
A very quick one.
I think you're very right. We have to really change the mind shift. Because as you say, Professor Sutton as well, you said that we see wastewater treatment plants as waste. And that's the problem that we have in for many materials. So we have to see what we have seen as wastewater treatment plants today as resource plants. They are really resource plants. There are a lot of resources that we need in the society in the wastewater treatment plants. So let's stop talking about wastewater treatment plants. Let's talk about resource plants, because that's really what they are.
Can I come in just there?
Yes, a very quick one.
Yeah, I think we're reinventing even the word waste. You need a reinvention of the regulations to enable your business. So a wastewater plant is a resource plant. I would say that which today the European regulations call waste is not waste, it's resource. And that which they don't call waste is waste. So if you have ammonia air pollution, I call that waste. It's been wasted. And so that's why when we talk in the Colombo Declaration, the goal to halve nitrogen waste, we don't mean a resource that can be used, we mean the losses, the sum total of everything that is wasted. So we need to transform our minds in many ways, including the language.
Thank you so much. I think we can go on for hours talk about this, but on Tuesday the 9th in the morning, we will have a session about the conversion of wastewater treatment plant into resource treatment plants. That will be held on the Nordic Ministers' Council's arena, so please come back then. The nitrogen question, we will support you as much as we can, because we believe that our solution will not only catch the nitrogen, it will reduce the cost for each wastewater treatment plant as well. And that's where we have the possibility to implement it. When the costs are lower, then why don't you buy it? So, but that we will come back to during the next COP, because we will definitely be here again and try to convince more countries to focusing on the nitrogen. That's a promise from my side. Thank you so much, Professor. Thank you so much, Anna. And thank you so much, the audience here and all the viewers on YouTube. See you again on Tuesday morning.